So this unweighted graph is done, and now let's move on to the weighted graph. I'll name it only graph.ts. So this weighted graph, this time now your edges will also have the weights. Alright. So, but before that, I just wanted to check on one thing. If I add a getter method, get vertices, like map t set t vertices, okay, duplicate function implementation, get vertices, get raw vertices, okay. So like how will it look like? I comment that u graph dot get raw vertices. If I run that, see, this is the visualization of the graph, okay, the unweighted graph. This 1 in this set, 2 and 3, 1 and 3, and 2 and 1. Alright, now let us implement the weighted graph. The weighted graph class graph accepting the type T, right? Highway vertices will now have type of map having T and again a map having T and again a map number. Now, if it is directed or not. Now what I'm gonna do is that I will add a constructor boolean false. Now vertices equals to new map and is directed equals to is directed. Alright. Now add vertex t void if we do not have this vertex, then only we are going to add. And the initial value will be the new map only, as you can see from the types. Alright. Now add h source destination weight. Default value is 1. Okay, and this will also return nothing, so return void. And now first let's add the vertex. Source sorry, this dot add, it's a vertex basically. Yeah. Now what I'm gonna do is that I will check for source dot set destination and its weight, and if this is not directed, then the two-way thing. Okay, wait. So yeah, if it is not directed, like, then we are setting this destination to the source as well, establishing this connection. Now we have our method of the remove vertex. So remove vertex, and here if it does not have vertex, then return. Now remove all the edges pointing to this vertex. And then finally delete this vertex. Right? Now the remove edge functionality. Right? Source T, destination T. Okay, the weight will not be required while removing, because it's just a value. If vertex dot has, it does not have source, or if does not have destination as well, then this function will not do anything. Otherwise, so we will be copying this here, delete, like this. Okay, that is how you do. Now we will be implementing the get all vertex method. Okay, so in order to get all the vertex, or simply get vertex, array dot from keys return. Okay, like this. Now let's implement the get edges function to retrieve all the edges. I'll create a new method get edges. Here, how you are going to get edges? Key number, okay, and a 2D array in which the inner array contains 3 elements. Okay, now edges, same thing, t number is to like empty array for const vertex neighbors of vertex const neighbor weight of neighbors. Okay, what you're gonna do, if it is directed or vertex is less than the neighbor, then what you're gonna do is that edges dot push vertex neighbor weight. Okay, and you return the edges. Now what we will do is that we will get all the neighbors. So get all the neighbors of the vertex. Then again a 2D array. This dot vertex dot has vertex. If it has the vertex, then array dot from vertex dot get vertex, all the entries of it basically, otherwise an empty array. Now we need to check if it has the vertex. Okay, so yeah, we can copy some functions from here to here. Alright, as vertex, as edge, get edge weight. Source P, destination T, number of undefined, return vertex at source vet destination. Alright, so this destination will contain the value of weight. Great. Now we are going to implement the BFS, the breadth first search, and let me tell you, the breadth first search here has to be very similar. So BFS start t end if it doesn't have this vertex, return an empty array. Otherwise, once visited equals to new set t like this and first result t like this, and we will maintain a queue. And visited dot add start. Alright, so while queue dot length greater than 0, we take the current vertex by removing one element from the queue. Result dot push vertex. Now for const neighbor of this vertex, if we still haven't visited, visited dot add neighbor and queue dot push neighbor. Alright, like this, and then simply return the result. This is how you do the BFS. So first you keep track of the visited, and since the start is already visited, so like you add it to the visited and then you maintain a queue. So there you track the current vertex, and then as long as we are able to have the element inside the queue, it will keep running, and then we will check it. We will be checking all the neighbors, we will visit them as well, and then we will be returning the result. Now let's do the depth first search. Okay. Oh, sorry, EFS start t like this if vertices dot has start. Alright, so I mean if it does not have this vertex, then return an empty array. Alright, now what I'm gonna do is I will keep track of the visited, like this, result like this, and now our helper function vertex T visited dot add vertex result dot push vertex and for const neighbor of vertices dot get vertex. If you haven't visited this neighbor, run the entire function on it again like this. Helper star turn result. This is how you do the DFS. Okay, so DFS uses the recursion basically. Now we are coming to a very important thing. This is the Dijkstra's algorithm. Dijkstra's algorithm, D-I-J-K-S-T, right? Dijkstra. So before that, we need to understand what exactly is Dijkstra's algorithm. Dijkstra's algorithm is used to find the shortest paths from a source vertex. Alright, the shortest paths. I mean, this is being used by Google Maps as well. So now, what we will do is Dijkstra start vertex like this. Okay, it will return map here. Sorry, D and distance, number, paths or path, maybe like this. Alright, like this. So if it does not have this vertex, then return an empty map. That's it. So distance is equals to new map T we can copy that like this. Okay, now visited unvisited. So this time we will also keep track of the unvisited. Alright, now initial distance will be set to infinity and paths will be empty. sorry, like this. And all of these are unvisited. After this, what I'm going to do is that the distance to the starting vertex will be set to 0. Okay. Now, while we still have unvisited, so this is something, let me explain. So, see, unvisited or size means, you added all these vertex to the unvisited ones. Now you are tracking all these unvisited ones. Now, as long as you have the unvisited vertex, you are going to do an operation. Means first you will find the unvisited vertex with the smallest distance, right? And then you will mark the current vertex as visited, and then you will update the distances to the neighbors. Alright. Okay, so let's start implementing that. That current vertex t or null equals to null. Let smallest distance equals to infinity for const vertex of the unvisited ones we will extract distance from here. Okay. Check the distance of the vertex. Now if it is less than the smallest distance, then current equals to the vertex. Alright. Now if the current vertex is null, then no more ritual vertex are there. So if then break this loop. Okay, now we will be marking the current vertex as visited. So like this, and now we will be updating the distances to the neighbors. Of vertices.get current if we haven't visited a neighbor, so const current distance equals to distances.get current dot distance, and new distance, current distance plus weight. Alright. Now, if new distance is less than, okay, this neighbor's distance, then a new path basically. Like this. Okay, so this is the new path. We select the paths, paths from this current vertex, and then you pass this neighbor. Okay, now distances are set neighbor and new distance and path, new path, like this. So you updated the distances to the neighbors, and finally what we are gonna do is that we are gonna return distances. This is our whole Dijkstra's algorithm. Let's go through it again so that you understand it completely. First, we created a distances map. It has distance and the path. We maintain the visited and non-visited. Now, we map through all the vertex, alright? And then, initially what we do is that initial distances are set to infinite and empty paths. Okay, we are just setting up our data. And now, for the start, we are setting the distance to 0. And the path is in the start only. Now, while the unvisited size is still greater than 0, means there are still some remaining to check. What you're going to do is that you have this current vertex pointer and this smallest distance. Now, for all the unvisited vertex, you check the distance and you set the smallest distance. Now, when you find the smallest distance, you also update the value of the current vertex in the parent to the current vertex in the loop. After that, if the current is null, then no more vertex to check. Now, you mark it as visited. You mark this current as the visited. Now you check all the values present for this current vertex. Alright. Now all the values, you check the neighbors and weight. And here, if you haven't visited the neighbor, what you do is that you first maintain a current distance. Alright. You first maintain a current distance and you have a new distance where you add the weight. And now here the current distance from this current value. From the map distances to get the current from the current vertex, and then you check the distance. Now if this new distance is still less than the neighbor's distance, then you set the value of new path as well, and then you update the value of this neighbor. Okay, so new path will be all of this distances from all of these paths from this current vertex and then this neighbor, and this is how you set it. Alright, this is the whole point of the Dijkstra's algorithm. This is how you find the shortest path. So you will get visualization when you will be using it. Now what we are going to do is that three easy methods we are going to implement. We will be copying those from here like this to here. That's it. Now let's use it. First graph equals to new graph, number based graph again, because it is the easiest to test. Add edge 1, 2, 4. Dot add edge 2, 3, 2, and again 3, 1, 1. So now let's console log graph dot get vertices. Alright, maybe get raw vertices will be the better one, because like here I copy this, and here I will be updating this and get raw vertices. Let me run this for you. You see, this is how a weighted graph looks like. Alright, so you have this 2 to 4, 3 to 1. Now these weights have been set. 2 has this weight of 4, 3 has this weight of 1. Alright, and now the shortest paths basically equals to Dijkstra starting from 1, shortest paths. You see, these are the shortest paths. Alright, so yeah, this is the complete implementation of the weighted graph. And now our graph section, the graph part is also complete. Now we'll be moving to the hash table. Thank you for watching.